This is a re-recording of a webinar presentation I made on the 8th of January 2024 as part of the Danish GrassTools project. The presentation is largely the same as the one I gave during the webinar, but I have expanded or rearranged some slides to address some of the comments made by participants. The motivation for considering how to account for carbon sequestration arises from my interest in farm-scale modelling. As part of this modelling, I wanted to calculate the greenhouse gas balances, and to do that, I needed to calculate the global warming effect of methane and nitrous oxide, and then subtract the reduction in global warming due to carbon sequestration. To do this, I needed to use a common metric. In this case, that meant carbon dioxide equivalence, which here we can shorten to CO2e. However, this turned out not to be a straightforward exercise, so I hope this presentation will help you understand why. The presentation is in two parts, with the first part dealing with the principles behind the calculation of CO2 equivalents, and in the second part dealing with the consequences of repeated inputs of organic carbon to the soil. So why CO2 equivalents? Well, CO2 equivalents enable us to express the effect of different greenhouse gases in one metric. This is necessary if we wish to add up the warming effect of the different greenhouse gas emissions and then subtract the cooling effect of carbon sequestration. It entails the conversion of emissions of non-CO2 gases to the equivalent mass of CO2. To do this, we need to multiply the mass of each non-CO2 gas emitted by its appropriate global warming potential. The global warming potential of a non-CO2 gas depends on the warming effect of that gas integrated over time and relative to the warming effect of CO2 also integrated over time. The global warming potential of a non-CO2 gas therefore depends on several factors. It depends on the rate of the depletion of that gas from the atmosphere after it has been emitted, the rate of depletion of CO2 in the atmosphere, the global warming effect of the gas, and the global warming effect of the CO2. And finally, it depends on the period over which the calculation is made, which is here called the time horizon. Now, nothing lasts forever, and that includes greenhouse gas emissions in the atmosphere. So all greenhouse gas emissions are lost to the atmosphere over time. Some are mainly depleted by chemical reactions in the atmosphere, and that includes methane. So if you look at the red rectangle, you can see that methane is mainly decomposed chemically in the atmosphere. Other greenhouse gases are depleted by an interaction with the Earth's ecosystem, and that includes carbon. So what you can see here is that CO2 in the atmosphere is depleted by both chemical and biological processes occurring over periods that range from months to centuries. Now here we don't need to go into the details of those processes, but we do need to be aware of their combined effect. Recall that the global warming potential of a gas is the warming effect integrated over time and relative to CO2. The global warming potential of a gas over time horizon T is the ratio of the absolute global warming potential of the gas over time horizon T and the absolute global warming potential of CO2 over the same time horizon. So what are absolute global warming potentials? The absolute global warming potential of a given gas is the warming effect of a pulse emission of that gas integrated over the time horizon. That means it depends on the mass of the gas that is remaining in the atmosphere at any given time t, the so-called impulse response function, or IRF. and the warming effect of that gas, AX. Expressed mathematically, it looks like this. In other words, it is the total warming effect of 1 kilogram of the gas over the period from its emission to the end of the time horizon. The important thing to remember here is that it considers a pulse emission, so a one-time emission, and the effects that are integrated over time. This method of calculating CO2 equivalence has some interesting consequences, as illustrated here by CO2 and methane. The scale on the right-hand side shows the absolute global warming potential. Since CO2 has a long lifetime in the atmosphere, its global warming potential continues to rise for centuries. In contrast, methane has a short lifetime in the atmosphere. Since it is a very powerful greenhouse gas, its absolute global warming potential rises steeply. And note here that the value shown on the graph has been divided by 10 in order to fit into the same scale as the CO2. However, as most of the methane is lost from the atmosphere within 1 to 2 decades, it quickly reaches a plateau. This we can see here. So from around this point, none of the methane remains in the atmosphere, so that we have a flat line. Since the global warming potential of methane is the ratio of its absolute global warming potential and the absolute global warming potential of CO2, it has a high initial value, and then that falls steeply with time. When we report greenhouse gas emissions under international conventions, we convert non-CO2 greenhouse gas emissions to CO2 equivalents using a time horizon of 100 years. The choice of 100 years was a political compromise made back in the 1990s. Although there have been arguments for the use of alternative time horizons, the considerable inertia associated with international agreements means that they are unlikely to have any chance of gaining traction with national governments. It's important to note that the emission of greenhouse gases for reporting are calculated annually, and the calculations are made separately and independently for each year. This means that the integrated warming effect is calculated from the year in question and then 100 years into the future. It also means that the time frame for the emission estimate moves forward 1 year each year. So, for example, the emissions calculated with the global warming potential 100 in 2024 are for the period 2024 to 2124, and in 2025 will be for the period 2025 to 2125. If we return to our earlier diagram, it means that the reference time frame moves to the right 1 year at a time. If we wish to calculate a greenhouse gas balance, we need to know the extent to which the carbon sequestration offsets the effects of the direct and indirect greenhouse gas emissions. For agriculture, the direct and indirect greenhouse gas emissions are mainly in the form of methane and nitrous oxide. If the calculation of direct and indirect greenhouse gas emissions uses a global warming potential approach, then these global warming potentials are based on the time integrated global warming effect relative to CO2, as we've seen earlier. If we want to calculate the offsetting effect of carbon sequestration, we must use a method that is based on the same approach, i.e., its effect on time integrated global warming. Whereas emissions of direct and indirect greenhouse gases are considered to occur wholly within the relevant accounting year, the organic carbon input to the soil is re-emitted as CO2 over a prolonged period. The offsetting effect of carbon sequestration results from the reduction in the time integrated warming caused by this delay in re-emission. If the amount and quality of carbon input to the soil remains constant, the soil environment also remains constant. And then the time profile of the re-emission of that carbon from the soil will also remain constant. If this is the case, then for the annual greenhouse gas emission calculations, the offsetting effect of a given input of carbon in crop residues or manure will also remain constant with time. There is no soil carbon saturation effect here, as each year is treated independently. However, as mentioned before, the time frame advances 1 year each year. We'll return to this issue in part 2. Turning now to the steps needed for calculating the carbon sequestration offset, we can refer to the paper produced by Peterson et al. In 2013. The first step is to calculate the absolute global warming potential of the mass of carbon input to the soil as if it were emitted instantly to the atmosphere. The next step is to calculate the emission of the sequestered carbon over the period from its input to the soil until the end of the time horizon. Here we will use the symbol theta to represent the emission at any given time. Step 3 is to calculate the absolute global warming potential effect of theta from the time of its emission until the end of the time horizon. Step 4 is to sum all these warming effects to obtain the absolute global warming potential of the sequestered carbon for the relevant time horizon. And step 5 is to calculate the global warming potential of the sequestered carbon, that is, the reduction relative to the pulse emission. This is expressed mathematically here. So here we have the absolute global warming potential of the pulse emission on the left, and on the right, the absolute global warming potential of the sequestered carbon. Those of you with good memories will recall that the calculation of the absolute global warming potential includes a factor AX, which is the global warming per unit of mass of gas. However, since we're only considering CO2 here, we can ignore this factor and express the absolute global warming potentials in terms of carbon alone. What you see in the bottom part of this graph is the amount of carbon remaining in the soil over time after the input of 100 grams of carbon in crop residues. The decomposition of the organic carbon leads to the emission of carbon in CO2, and this is what you can see in the above, on the top part of the graph. Remember that theta is the mass of carbon emitted as CO2 each year. So here we can see that theta 0 is the carbon emitted during the first year. Similarly, theta 1 is the carbon emitted in the second year. Note that most of the carbon that is sequestered is emitted within the first 1 to 2 years. The remaining carbon is emitted over a period of decades and centuries. Here we're looking at the fate of that soil carbon after it enters the atmosphere. The first theta here is the carbon emitted in the first year, and it is progressively removed from the atmosphere over time via the processes we outlined earlier. The second theta is the mass emitted during the second year, and it too is depleted over time. This is then repeated for every year until the end of the time horizon. The absolute global warming potential of the sequestered carbon is the sum of all these curves for all the years until the end of the time horizon. This is expressed mathematically here. To calculate the offsetting effect of carbon sequestration, we need to calculate the difference between the amount of CO2 in the atmosphere following a pulse emission, shown here in orange, and the amount following the sequestering of carbon in the soil, shown here in blue. With the pulse emission, the amount of CO2 in the atmosphere falls over time as it's depleted by the mechanisms we outlined earlier. With the sequestered carbon, the amount initially rises as the amount as the carbon in the soil is mineralized and emitted from the soil, but then it falls as the rate of emission falls below the rate of depletion. If we join the tops of the columns in the previous graph, we get this figure. Remember that the absolute global warming potential of carbon sequestration depends on the difference between the pulse emission and the emission of the carbon that's sequestered. The absolute global warming potential of the pulse emission is shown here in orange, and the absolute global warming potential of the sequestered carbon is shown here in blue. The difference is shown here in green, and it represents the reduction in the integrated warming effect of the sequestered carbon. To calculate the carbon sequestration offsetting in CO2 equivalents, we need to multiply the amount of carbon in the residue, or manure, by a factor that converts from carbon to CO2, and then by the global warming effect, warming potential of the carbon sequestration. Under Danish conditions, this is equivalent to around 9 to 10% of the crop residue carbon input when using a time horizon of 100 years. It will be greater for manure carbon as some of the carbon is stabilized in manure storage. Peterson et al. Estimated the value to be approximately 0.2 tons of CO2 equivalent per ton of crop residue carbon input. However, the range of offsetting in Danish agriculture remains quite uncertain due to uncertainty about the size of the carbon inputs and the extent to which manure carbon is stable during storage. In general, carbon sequestration offsetting is likely to be significant but not decisive. You can expect a large variation between farms. The largest offsetting will be where there's a lot of grass, but at the moment at least, that's also where there'll be a lot of cattle and so a lot of enteric methane emission. Just to make things more complicated, increasing the input of crop residues or manure impacts soil processes, in part because nitrogen is added along with the carbon, so nitrogen mineralization increases, and partly because organic matter increases the water holding capacity of the soil. Both of these processes could potentially increase the yield and production of crop residues. And the increased nitrogen mineralization might also lead to an increase in nitrification and denitrification, and therefore increased direct and indirect N2O emissions. Finally, it's unrealistic to expect that the climate will not change over the next 100 years. And that means that the time profile of emissions of the soil will also change. And the depletion rate of all the greenhouse gases in the atmosphere will also change. So if we can conclude for part one of this talk, global warming potentials include an integration of global warming over time. If the global warming potential is used to calculate the direct and indirect greenhouse gas emissions in terms of CO2 equivalents, then the calculation of carbon sequestration offsetting has to use the same approach. The global warming potential for soil carbon sequestration must take account of the time course of carbon emissions from the sequestered carbon, and this will vary according to the soil climate, and in other words, will be depending upon site and management specific factors. The global warming potential will also vary depending on the quality of the carbon input. The assumptions underlying the calculation of the global warming potential of carbon sequestration are not valid because adding organic matter to the soil leads to more than just carbon sequestration, and because the climate will change. Moving now to part two, looking at cumulative carbon inputs. We assume in this method that the input of each carbon annual input follows its own decomposition path over time. It's not strictly correct, but it's not usually too incorrect. I want to illustrate this with a simplified example. So this example includes the assumption that all sequestered carbon is emitted within 5 years. We input 100 tons at the start of each year. Any carbon emissions occur at the end of each year. And the emission of soil carbon from each input over years 1 to 5 is fixed at 50%, 20%, 15, 10, and 5% in that 5th year. What that looks like if we plot it is this decay curve. So with repeated carbon inputs, at the start of year 1, we put in 100 tons, but by the end of year 1, half of that has been emitted. But then we add another 100 kilograms at the start of the next year. But by the end of that year, half of that has also been lost, plus some more of the carbon that was input in the first year. So we keep on adding carbon each year. And what you see is we build up a family of decay curves. What you can also see is that after the 5th year, all of the carbon input from the first year has been lost. So after that, this pattern just repeats itself year after year. So the total rate of carbon emission is the sum of the rates of carbon from each of the earlier years' inputs. So in the first year, the total carbon emission results from the first year's input. In the second year, the total carbon emission is the sum of the emission from the first year and second year. And likewise, until we get to year 5, from there on, because the pattern of emission just repeats itself, the total emission rate remains constant at the rate equivalent to the rate of carbon input. So if here we have the rate of emission and we're inputting 100 tons per year, in blue, what we have is the net sink of carbon into the soil, falling to 0 at year 5. If we plot the carbon storage with time in the orange on the right-hand axis, you can see that it too reaches a plateau at year 5. Recall that the pattern of carbon emission from each year's carbon input is the same, and that means that the global warming potential of the carbon sequestration is also the same in each year. That means we have the counterintuitive situation in which in the annual accounting, the offsetting value of the carbon sequestration remains constant with time, but the CO2 emissions and the carbon storage do not stay constant with time. If we now look at the effect of soil sampling and use, again, the simple example, if we imagine that we can sample the soil after periods ranging from 0 to 10 years, and then calculate the annual average change in soil carbon storage. Then we use this average to calculate an apparent rate of carbon sequestration in CO2 equivalents. So if we calculate the average rate of carbon storage, we see it falls progressively over time, starting at the 100, which is what we're actually putting into the soil each year. It falls progressively. Remember that after year 5, there is no net increase. But because we are calculating over a longer and longer time period, then this average rate of carbon storage continues to fall with time. If we then use that information to calculate an apparent CO2 equivalent, it also falls in the same fashion. The actual offsetting effect with this example is much smaller than the calculated effect here for a time horizon of 100 years. But remember that this is a very artificial situation with a very short period over which the carbon is emitted to the soil. In reality, the difference would be much less, but the example serves to highlight the problem that arises if changes in soil changes in stored carbon are interpreted incorrectly with regards to offsetting. So if the carbon input and profile of organic matter decomposition remains constant over time, soil carbon storage will reach an equilibrium. The change in soil carbon storage over time cannot be used directly for calculating the offsetting against greenhouse gas emissions if the calculation of greenhouse gas emissions uses a global warming approach. That does mean that the reporting of carbon storage changes in the land use change reporting cannot be used directly. Measured changes in soil carbon storage could be used indirectly with additional modeling, but only with some knowledge of the historical land use and management. We could find ourselves in a situation where historic land use and management could mask the current carbon sequestration. So, for example, one could find a situation in which carbon storage is falling, even if carbon sequestration is increasing. Now, a few wider considerations. The overriding target is holding the increase in the global average temperature to well below 2 degrees C above pre-industrial levels and pursuing efforts to limit the temperature increase to 1.5 degrees C, as stated in the Paris Agreement. Net zero, either in terms of CO2 or CO2 equivalents, is not mentioned in the Paris Agreement. As the Climate Commission in Denmark has pointed out, the effect of a given emission measured in CO2 equivalents on global temperature depends on the proportion of the individual greenhouse gases in that calculation. This means that achieving net zero, either in terms of CO2 or greenhouse gas emissions in CO2 equivalents, does not mean that we have complied with the Paris Agreement. So where does this lead us all? Well, the assumptions underlying the calculation of the carbon sequestration offsetting are not strictly valid. However, that's also true for the calculation of the global warming potential of methane and nitrous oxide. This global warming potential CO2 equivalent approach is useful in that the advantages associated with simplicity and transparency outweigh its inaccuracy. That's also true if we apply it to carbon sequestration. However, it means that we need to be careful how the CO2 equivalent of carbon sequestration is calculated and then used. Nevertheless, the main issue with carbon sequestration is in uncertainty concerning the quantity and the quality of the carbon inputs. So some final conclusions. The CO2 equivalent approach is an imperfect metric, but it's useful where there is a need for simplicity and transparency. For example, in international and farm scale inventories. Methods for calculating the offsetting value of carbon sequestration need to be consistent with the method used for the direct and indirect greenhouse gas emissions. Measurements of soil carbon storage over time need additional modeling if wishing to calculate the carbon sequestration offsetting. And achieving net zero, either in terms of CO2 or greenhouse gas emissions in total, does not mean that we have complied with the Paris Agreement.